Okay, so this is a continuation of section 6.1. In first lecture and 6.1, we talked about number theoretic functions in general, and then we introduced the number of divisors and sum of divisors. Okay, and studied some of their properties. Now let me begin right there. Let's assume that let n and m be relatively prime. Relatively prime positive integers. With the prime factorization. N is equal to P1, alpha 1, P2, alpha 2, and so on, PR, alpha R, and M equal Q1, beta 1, up to QS, theta S. Where these, the alpha i's is between 1 and, so we don't have a restriction on these. All I have is the alpha i's bigger than or equal to 1, and the beta i's also bigger than or equal to 1. But what we have, since these two positive integers are relatively prime, we have, and the pi does not equal to qj for any I and j. And these are between, of course, the I is between 1 and R, and j and the j is between 1 and S. So these are relative. Then if I look at tau of nm, all right, so this is going to be tau of putting the prime factorization like this, and then multiply this is by the q1 up to q s, and this is beta 1, beta s. We could think of this as one number, of course, and this is the prime factorization of it, which is mn, of course. And now, from the way we proved or find the formula for tau of, in terms of a prime factorization of the number, we know this is equal alpha 1 plus 1, alpha 2 plus 1, up to alpha sub r plus 1. And also we take the product of the beta 1 plus 1, and so on, up to beta s plus 1. And then we could actually think of this as one factor in here, which is the product of all the alpha I plus 1, and this is another one, and this one is nothing but actually tau of n, and this is tau of m. So in other words, we have tau of nm is equal actually tau of n tau of m. That is true, provided that the m and n are relatively prime. These kind of functions, which we will define actually formally, this is an example of what we call a multiplicative number theoretic function. Similarly, when you look at the sigma, you will see the same thing happens. That is sigma of mn can be calculated in a similar way. Similarly, you look at sigma of nm and equal sigma of p1 alpha 1 p or alpha r. If we have more primes in here, the q1 beta 1 up to q s beta s. And all these primes are distinct. So when we apply sigma to such a prime factorization of nm, it will be the product, all right? Actually, let me write the product, two products, okay? Or one product, it's gonna, let me actually write it in detail. So B1, L1 plus 1 minus 1 over B1 minus 1. And for each one of the primes, the piece is alpha r plus 1 minus 1 over p to the r minus 1. And the same thing with the q's. So we have a q1 s1 plus beta. Beta 1 plus 1 minus 1 q1 minus 1. And the last term is the q beta to the s plus 1 minus 1 over s, and the qs minus 1. And then again, we will group these together like this. Here we get sigma of n, sigma of. All right. Now let's formally define the type of function that have this property, as such a property. And study some of their properties, and we're going to see they would simplify a lot of the work that we do with arithmetic or number flipping functions. Here's the definition. The number theoretic function equaling f is said to be multiplicative if for every m n in z plus such that greatest common divisor m n equal 1, then the f of m n is equal to f of m times f of m. So such function we call them multiplicative. On the other hand, f of m n is equal f of m times f of n for every m n and z plus. Actually, we could actually have this one is even for every integer. Don't have to be even restrict ourselves to positive integers. All right. So for every, this is true without restricting the m and n to be relatively prime. So if this is true for all integers, then f is called completely multiplicative. All right? So if no restriction, then we call it completely multiplicative. Let's look at some examples of multiplicative function, completely multiplicative, or functions that are neither one of these. Or say the identity function f of n equal n for every integer n is in fact multiplicative. It's completely multiplicative. So here's an example of every n in C is completely multiplicative. You see, this is very simple. For every m n in C, f m n, by definition, it returns the value that enter f, which is m n, but m also it is equal f of m, and n is equal f of m. So yes, no restriction on, or we don't require that m and n to be relatively prime. Okay, let's look at another example. G of n is equal to f. This is actually neither multiplicative or completely multiplicative. Well, in fact, every completely multiplicative function is multiplicative, of course. Let me actually put this remark here. So completely multiplicative function implies multiplicative, but not the other way around. So if a function is completely multiplicative, then it is definitely multiplicative. But the reverse argument is not true in general. All right, so if we look at this, you know, we can say G of Mn, we try to do this, this is going to be equal to Mn. And we look at G of M, G of N, this is going to be 2M, 2N, and this is 4. And there's no way these could be actually equal to each other. Because, you know, unless only for m and n is, you know, if it is equal to 0, all right, and it doesn't satisfy for all values, right? So we get these are different. Another example, if we take actually h of n equal n squared, we're going to see this is also completely multiplicative. And hence multiplicative. Okay, h of n equal n squared is completely multiplicative. That's very easy to see. All right. Other, you know, functions are completely multiplicative, like exponential function, but we, you know, when we talk about number-filtered function, this kind of, every function we could think of it as actually, as far as we restrict its domain to, you know, the set of integers, then it becomes a number-filtered. However, you know, our concern are for those, you know, functions that are defined in terms of divisors and things related to concepts in number theory, not in calculus or other you know, types of functions. All right, now we're going to study some properties of multiplicative functions. And these properties, of course, will hold for all completely multiplicative functions, and they might have some other properties themselves. Okay, so here are properties of multiplicative function. The first one is this, call actually number one. If is not the zero function. By the way, the zero function, as you know, as trivial as it is multiplicative. It's completely multiplicative. But zero function is the function that takes every n to zero. Okay, so this one is f of n equals 0 for all n in Z is called the zero function. So if f is not, means this one is not, then and okay, if f does not equal 0 is a multiplicative function, then f of 1 must equal 1. All right? Proof of this is like this. Since f is not identically equal to 0, this implies there exists at least an n in Z such that f of n is not equal to 0. Now let's consider this f of n. I can write it as, of course, n times 1. And we have the greatest common divisor of n, regardless what it is. And 1 is always equal 1. So, and since the function is multiplicative, okay, so this is f of n times f of 1. Since f of 1, sorry, f of n does not equal to 0, we can divide both sides of the last equation by f of n, and this would imply we have f of n over f of n. This is a legitimate number equal f of n by f of 1 over f of n. The f of n cancel all out, and then we end up with 1 on the left-hand side equal f of 1. Yeah, that's it. Okay, let's look at another property, which simply say that states that to evaluate a multiplicative function for an arbitrary integer, you can only find the value of the multiplicative function for powers of prime. And then this would give you completely determine the value for any integer. Okay, so this theorem is, or this property is stated this way. If f be a multiplicative function, and you're going to let n equal I equal 1 up to r to I case of I. Be the prime factorization. N, that is a natural number or a positive integer. Then f of n is equal the product I equal 1 to R F of Bi K sub I. All right? Again, this means F of N is determined, or if you wish, or calculated, calculated completely by the values of F on powers of prime, F on the powers of the prime factors of F. All right, so completely determined means once we know F for every power of a prime, then we know it for F. Okay, unique. Give us unique value. All right, let's go ahead and actually prove this. And the proof is actually by induction on the number of different prime factors. All right. Proof by induction on R, that is the number of distinct prime factors on. So if I equal 1, means we only have one prime factor, then N is going to be B1 times K1, all right? And F of N is equal F of B1 K1. And this is the trivial sort of product. So this one holds. Now, let's assume that the theorem or the property holds for any N with R distinct prime factors for some are bigger than or equal to 1. Now I'm going to consider that N be an integer with R plus 1 prime factor. So then we have N equal D1 K1 E R plus 1 and K R plus 1. when all these primes are distinct, okay? Now let's look at f of n, which is equal to f. I could separate the prime factors in here into this up to p r k sub r, and then p r plus 1 k r plus 1. Now, since these primes are distinct, then they are relatively prime, okay? So, which means that the first product, greatest common divisor with the second single prime to the exponent, of course, give us 1, okay? Since the PIs are distinct, this implies greatest common divisor of P1, K1, P R K R. But think again, this is of an integer, and P R plus 1, K R plus 1. This is equal to 1. Now, with f being multiplicative, implies that f of P1, K1 of PR, KR, okay, times PR plus 1, KR sub R plus 1. This is just the product f of the first. It's a lot of writing. R times f of PR plus 1, KR plus 1. All right, now we're going to use our induction hypothesis to express that as so by induction hypothesis, we have this one is the product of I equal 1 to R f of B sub I K sub I, and this one is f of B R plus 1 K R plus 1. Now we can use or rewrite this as I equal 1 to R plus 1 of f B sub I, then K sub I, and this will take care of it. All right, so we have the theorem is, of course, is true for R plus 1 by math induction. The property holds for any positive integer n. All right. Now, on the light of this, we can see that we have an easy way to calculate and actually prove the formulas for number of divisors and sum of divisors. Okay, so let's revisit those. First of all, we know these are actually multiplicative. We sort of have shown that, all right, earlier. Just I should have indicated that. Okay, now since tau and sigma are multiplicative, then we have tau of n, all right, is equal to the product, all right, of I equal 1 to R of actually tau at the P sub I and K sub I. All right, and the same thing for sigma. P sub I, K sub I. So in other words, now in order to find the formula for this, we need to know what this one is. Since this, now the number of divisors, remember that's what tau is, number of divisors of a power of a prime is going to be 1, p squared, and so on. So this one is in fact equal ki plus 1. And when we put this together, with this is being multiplicative, means I equal 1 to n of k sub I plus 1. And this is the formula which we have for the tau. Similarly for the sigma P I K sub I, this is the sum of the divisors of a power of a prime. So we could have 1 when the K sub I is equal to 0, then we have P, then we have, let me put I squared up to the I to the K. And then using the geometric series sum, which we say that this one is equal to the I Ki plus 1 minus 1 over Pi. And now together with the product, we come up with the formula. All right. Now let's proceed to talking about more properties of multiplicative functions. The third one is the the product of two multiplicative functions is multiplicative, not the sum. The sum is not. And the quotient. Okay? So this is number 3. If F and G are multiplicative, then A, if G is multiplicative, 2, F over G is multiplicative, of course provided that G of n does not equal to 0 for any n. Okay. The proof of the first one is the second one is similar. Again, let m, n, and z plus, or z actually, such that greatest common divisor is equal 1. Then I'm going to let also h of n is equal the product of these. H is actually equal the product. We put this h equal f g. Now let's look at H M N. This is by definition of the product of two functions is we evaluate each one of them at Mn and G of Mn. This is by definition of a product of two functions. Now the Fmn, because this is multiplicative, we can say this is F of M. F of n, the same thing with the G And since the values of these are in complex numbers, these are complex numbers, you can switch things around if everything is commutative. So you could rearrange this and write it as f of m, g of m. Then we have f of n, g of n. Which means that we have this one equal to the f of m, g of m, this is equal h of m times h of n. And that's what we have there. H of mn equal the product of the individual values of the function h. All right, let's look at some more properties, actually more important ones. And but before we do this one, we need a lemma in between. Okay. Here is a lemma which tells us about we have two relatively prime integers, how their divisors are related in terms of the product of the two numbers. All right. Let m again and n be relatively prime. Integers. Then if d1, let me see how exactly I want to state actually this. Yeah, I want to state this slightly different. Then the divisors, the set of divisors of mn consists exactly of numbers of the form d1, d2, where d1 is a divisor of m and into d2 is a divisor of n. To put it in simples, it means that the set of divisors of mn means d, such that d divides mn. Let me say actually here. The set of divisors d in z plus such that d divides mn is the same as the set of divisors d1, d2 in z plus such that d1 divides m and d2 divides n. So this is the set of divisors of mn. This one is the d1 is the divisors of m and d2 is the divisor. So if you multiply them, all different products of the different divisors, we get these two sets to equal to each other. All right? And the proof of this actually does follow from the, the theorem at the very beginning that we proved, which tells us, how the divisors of a certain number are. Okay, so here's the proof. So let's assume that n or m is equal to, let me use actually P1 alpha 1 up to P sub R alpha R. And the M is going to have, the N, sorry, has different prime factors because they are relatively prime. 1, beta 1 up to the Q sub S, beta sub S. So these are, we're going to assume that these are the prime factorization of M and N. Of M and N. And we have, of course, the Pi does not equal the Qj for every I and j. Now, let's do the, the divisors of the product, okay? And let's take a divisor of the product and then see how it is related to the divisors of the M and N individuals. So let D be a divisor of M and N. This implies by theorem, I believe it is 6.1, that's the very one we have at the very beginning. Let me check. Was it the first one? Right. Okay, so 6.1 implies that D is going to equal all the primes that appear in the prime factorization of the product, which is going to be B1, K1, B2, K2, up to P, KR. And we use the Q1, L1 up to QS, LS, where these case of i's bigger than or equal to 0, less than or equal alpha I, and the L sub j on the Q's is up to this one, less than or equal to beta sub j. All right. Now, also we could write this one as D1, D2, and these are where, of course, D1 is just the product of the primes, the P's. Is a divisor of M and when I take D2 and D2 is equal Q1 L1 up to QS LS is again is a divisor of M. So every divisor of Mn is actually a product of two divisors, and the converse of this is also actually true. All right. And actually, you know that we are also the D's are here going to be relatively prime. Moreover, the greatest common divisor of D1, D2 is equal actually to 1. So, this is actually one direction, means that we proved that every D, every element in the set of divisors of Mn is, actually belongs to the other set, which is the product of divisors. The argument is reversible, means if we have a divisor, D1 of M is going to have this form, and D2 of M is going to be of this form, and when you multiply these, you come up with a divisor of the product. Okay, so it's kind of very straightforward. All right, now we want to present one important result that we're going to be using many times. And we're going to define a new function in terms of another function. And we're going to do this one actually in a form of a theorem. In other words, the content of a theorem. 6.4. If f is a multiplicative function, then the function f given by f of n is summation of f of d, d divides n, is also multiplicative. Actually, this new function, the capital F, can be defined for any, okay, for any number theoretic function. We are interested in the case where the f is multiplicative. In other words, we can define such a function without f being multiplicative. All right, so here's the proof. Actually, the proof it follows immediately from the lemma. But let's understand how the f, the capital F, of course, of n is defined. So we're going to add up all possible values of f for the different divisors of n. That's what this notation means. The summation is over the possible divisors. Okay? So again, let's start with, we're going to show that with m and being positive integer, I thought integer doesn't have to be positive, okay? And greatest common divisor is equal 1. Then, let's look at f mn. By definition, this is divisor dmn of f of d. Just a different integer till we take the divisor. Now, this summation, which is taking over all divisors of mn, it is the same as actually f of d1, d2, okay, where d1 is a divisor of m and d2 is a divisor of n. So replace each divisor of mn by what is, the divisor that produces this d, which is d1 for d. All right, now since f is, we also have these are relatively prime, d1 and d2, just as we seen before, and this we can write it as d1 divides m, d2 divides n of f of d1 times f of d2. Now this is true because f is multiplicative and the greatest common divisor of d1 and d2 is equal 1 and f multiplicative. So that's why we have this equality. Now this sum is basically, we can write it also as this. So let's see how this sum can be written as. So that sum can write it as D1 divides M of F of D1 multiplied by the sum over D2. I'll illustrate this in a minute, and then once we have this becomes F of M, F of M, not D, and F of M. All right, let's look at why this sum is actually, we can split it this way. So let's say that we have that sum is F of D1, 1, all right, F of D2, 1, okay, plus F of D1, 2, this is a subscript, okay, superscript, it's not a square. And then this is F of D2, 2, and let me add one more, and then this is going to be, in other words, there are three factors, all right, for this. Some of these could be actually equal to 1, okay, we don't know. And this is F of D1, the third, and then F of D2, third. All right, so let's assume we have this sum. And what I'm saying is, this is the same as taking the F of D1 plus F of D1, this is 1, 1, okay? And this is 2, and F of D1 to 3. And now we're going to multiply these by F of D2, D2, 1, F of D2, 2, the second one, plus F of D2, 3. All right? And now when we multiply these out, all right, it's going to give us all actually the, let me think about this for a minute here. No, actually, I did this is wrong in here. Let me take this one out, okay? So let me take this product in here, the summation. So we have this. This D1 divides M, D2 divides M. And this one is F of D1, F of D2. Well, here we need to assume what the, if the possible values of, so if I say divisors of M, is D1 actually, let me put 1, 1, and then D1, 2, and D1, 3. And let's say the divisors of N, these only have 2 divisors, 1 and D2, 2. The summation, we are supposed to go over all possible values of these. So there is going to be the D1, 1 with D2, 1, and D1, 1 with D2, 2. All of these, we have to run this one, and then we have to go with D1, 2, D1, 2 to 1, and the D1, 2 with 2, 2. And then we go with the third one, D1 to 3, D2, 1, and D1 to 3, D2, 2. All right? So a total of 6. All right, when we're going to write this one, And then if you write them down, I don't want to go through with this. And then you're going to see that it would be the same, because this is going to have 3 terms in here, and this is going to have 2 terms. When you multiply, you get 6 terms. All right, so that's what it is. All right, now with this, we can present a simpler way to see that the tau and sigma are multiplicative. So I want to write this as a corollary using this theorem. As I said, we're going to be using this theorem quite often for proving some other functions, arithmetic functions are multiplicative. So here's the corollary. Tau and sigma are multiplicative. We know this, but we're going to prove it using the theorem. That's the idea. Now remember that tau of n, which is, this is the, what we call, this is number of divisors. Okay, so number of divisors, and we wrote this as this. All right, now let f of n equal 1, then I claim that tau of n is equal the, actually this is, sorry, not this one is equal to this. Not a product, it's a sum. That means we're going to add how many ones, and for every divisor we're going to count 1. But so if I let, you know, in the theorem, okay, let this one n of 1 in the theorem, then the f of n is going to be basically d divides n of 1, right? And but this is equal, of course, tau over 1, since f of 1, f of n equal 1 is multiplicative. In fact, it is completely multiplicative. It is multiplicative. This implies that f of n, which is equal to tau of n, is multiplicative. Similarly, for the sigma, if you recognize sigma of n as a sum, which we know it is, so sigma of n, you know, this is actually the sum d divides n of d. All right. So for this one, you're going to let f of n equal to n. This is multiplicative in the theorem. Then f of n is, by definition, is equal to f of d, such that d divides n. But f of d, this is the identity function, is equal just d. And by the theorem, this implies, and this is equal sigma, of course. So by the theorem, sigma is multiplicative. All right. And that's it. All right. So this is it for section 6.1. Hopefully, I will record another lecture on 6.2 and the remaining part of chapter 6. All right, stop right here.